So now let's consider another example. Assume we have a array of lights, on, off, on, off, on. So lights are either on and off. Let's make it a bit smaller. And now what you can do is you can choose a row and then flip the all, you have a switch here. If you click this switch, then all on becomes off and off becomes on. So it will become this. And also there is a switch on this each column. If you switch and click it, then all off becomes on and on becomes off. So this becomes so you could do the combination. So once you click this, then this becomes XO, XO, XX. And once you click this after that, then this becomes X, X, O, X, O, X. So you have this operation, and then you can ask that, can we, depending on the, so initial structure is given, initial configuration is given, let's say initial array is given, can we turn all the lights on? Or how many lights can you actually turn on? So this is one question. So one of the approach we can take is, we can again to randomly select whether to hit these switches or not, and then try to analyze the, analyze what you will actually, get. So let's make it a bit more rigorous. So we want to put it into a mathematical formulation. And instead of estimating the number of lights on, because if you have n by n array, you know exactly how many places, how many bulbs are here. So if you know that the number of lights on minus number of lights off, if you know this number, then you actually know each number, because you know the summation. Sum is n squared. So if you know the difference, then it's okay. Then you get the answer. So you consider the n by n matrix with entries. Aij is either +1 or -1. And let's say 1 indicates on and -1 indicates off. And we choose xi and yj, or I and j are the index indicating the row and column, with the number indicating whether we hit the switch. And these are either 0 or 1. If we note that if you hit it twice, then it's same as not hitting at all. Even if you hit one and then you hit other things and then you hit again, that's same as just not hitting both of them at all. So if we hit something in odd number, then it's 1, and something in even number, then it's 0. And let's say xi is row, and then yj is the jth row. So xi, yj. Then the following theorem says that we can do at least, this good. So our goal is to, recall that our goal is to turn as much lights on as possible. Then we can actually find xi and yj. Wait, sorry. Let me correct myself. We want to multiply. So let's write it 1 or negative 1. If we don't hit the switch at all, then we will multiply 1, which will not change nothing. But if you hit something at 1, something once, so let me correct. If you don't hit anything, then we will multiply 1, which will do nothing. If we hit the button once, then we will multiply negative 1, which will change the order sign. So on becomes off, off becomes on. So plus minus 1. Xi, yj are plus minus 1. So we can actually indicate, we can actually find xi, yj such that this number so if this is 1, if ij entry, the bulb at the ij position is on after applying according to this. And this is negative 1 if this is off. So you sum them up together, then you get the difference between number of lights on and number of lights off. Then you can actually make sure that this is at least this weird number times n to the 3 over 2. So you might wonder, where does this weird number square root of 2 over pi comes from? Give me a moment. And this actually comes from the estimation on the binomial coefficient, which we will see later. So what we do is we first forget x1 to xn. So for now, let's just forget all rows. Let's just assume that all of them are 1. Then we select y1, y2, yn independently at random. Independently, uniformly at random. From negative 1 or plus 1. Then you have this ith row, 1 plus 1. Let's just write plus, negative, plus, plus, negative, plus. Whatever this was. Once you multiply this, y1, y2, y3, and so on, then each of this entry on the row is either plus 1 or minus 1 with probability half in an independent way. So each ai j yj is plus 1 or negative 1 with probability half, and they are independent over j. So now let's say Ri is summation of Aij, Yj, j is 1 to n. So for given row, you do that, then you get this number and sum it up, that's Ri. Then let R be the summation of absolute value R, I is 1 to n. So why do we let this in this way? So this is the summation of the all entry. So Ri, you sum up all the entries on the row, and then you sum up all the entries on the row. And then once you add them together, then that's the addition of all the entries. However, we have not, we for now forget it, the row. So if the summation is positive, then we let xi be just 1. But if the summation is negative, then we will later let xi be the negative 1. So that you hit the negative 1, then this becomes non-negative. Because our goal is to maximize the sum of the entries. So every negative one, we will change it to plus. So that's why we add this absolute value. So this will be our final answer. So we want to maximize this R. And we know that because of this, the row vector ai1, y1, ai2, y2, ain, yn is actually uniformly distributed over all 2 to the n possible rows. So if you fix plus, 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 minus, plus, minus, plus certain row, the probability that this is the ith row after applying this, multiplying this y on the entry is exactly 1 over 2 to the n. So now our strategy is again simple. We want to consider expectation of this. And then if you know the expectation, then that provides a lower bound on the size of R. So that provides a one choice, which we have this R is bigger than this expectation of R. So we want to compute the expectation. So how do you compute it? Again, this is the summation of these. So we want to first find the expectation of the absolute value of Ri. Then we can consider, so because of this, we consider all the possible rows with exactly I positive. I many plus 1 and rest of them is minus 1. Then there are this many and each of them has probability 2 to the negative n. And then once there are I many positive and n minus I many negative, then what's the value? I minus n minus I, which is 2i minus n. But you have to be a bit careful because this is absolute value sign. Depending on I, you have to swap the sign. So let's just write n minus 2i and absolute value. So this is a probability. So this is the value. Let's say this is a value s. And this is the probability that the Ri is s when s is exactly n minus 2i. So let's say inside of this n minus 2i is s, and you take the absolute value. So which is the, so this is the value that it can take, the random variable can take, and then you multiply the probability. That's the formula for expectation. And you can now compute this. If you, this is, so you can actually, so I is from 0 to n, but it's symmetric, so you can only, add, terms up to half and then multiply 2. And you can actually check that this is same as summation of this. You can just rewrite each term in this way. And you can telescope. If you write these terms, so here, let's say n choose k is 0, if k is smaller than 0 or k is bigger than n. Then let's say it starts from 0 to n. Then let's just take out n, the common element. Then that starts from this minus this. And so on until n minus 1 over 2, n minus 1 choose n minus 1 over 2 minus n minus 1 choose n minus 1 over 2 floor minus 1. And this term cancels out, this cancels out, and then only one term left. And this is n times 2 to the 1 minus n minus 1 choose 2 under n minus 1 floor. And by using Stirling's formula, this is roughly square root of 2 over pi plus real of 1 times square root of n. So, you know this expectation, and by the linearity of expectation, what do we know? Expectation of R is square root of 2 over pi plus 0 of 1 times n to the 3 over 2. So now we pick xi with the same sign as ri. Then we have the desired summation is exactly same as R, and you get this number. And if you compute the number, so then this number is slightly smaller than 1. And we can ask that, okay, so we initially wanted to turn all the rights, but how many rights we actually turned on? So this shows that the number of rights turned on is like half of the n squared plus half of this number, which is n to the 3 over 2. So you might be a bit disappointed that this is much smaller than n squared, so it's subquadratic. So you can ask that, can you actually improve? So how tight is this bound? So one can show that improving this more than n to the 3 over 2 is impossible. So this number is a bit smaller than 1. We may be able to improve this to 1, but more than that is impossible. So this order of this term is best possible. Why? You know that there is this concept of Hadamard matrix. we know that this exists. And what's the Hadamard matrix? Let's say n by n Hadamard matrix exists. Say n is power of 2. And what's the Hadamard matrix? Is matrix with column vectors, let's say u1, u2, un, which has all the entries 1 or negative 1, which forms an orthogonal basis. So ui dot product with uj is 0. And none of them is 0. So we know that if n is certain number, then this exists. By using that, we can actually show that this above cannot be improved too much. First note that if A is Hadamard, then we have this u1, u2, un column vectors. And once you flip one, then ui becomes negative ui. But this is still Hadamard matrix, because negative ui dot product with negative uj is still 0 if ui dot product with uj is 0. And also if you flip a row, then ui dot product uj after the flipping, what is this? This is summation of ui l, uj l, L is 1 to n. But all the terms, so let's say you click the L primes row, then all the terms here are still same. And on the L prime term, ui L prime and uj L prime, this becomes negative, this becomes negative, so their multiplication is same. So this is still same, so which is still 0. So this switch, so no matter how you hit the switch, you always get another Hadamard matrix. But we know that if A is Hadamard, then the summation of all the entries cannot be too large. It's at most n to the 3 over 2, which always serves the purpose. Why does it hold? I mean, it's not too difficult. Instead of finding this, you squared it. Then by Cauchy-Schwarz, this is same as, I mean, you sum the interior ones. I mean, you divide the interior ones into many pieces, and then you sum each pieces. And then here is summation of 1 square, which is n. So you get this inequality. And you have I is n, say j is n. So inside of here, so you can write each aij is negative 1 or 1. If you squared it, it's 1. So you get n terms of 1 plus 2 times aij, ail, j is smaller than l. Which is, now you can actually compute. So there are n, and n terms of n you add, so n squared, and then there is n cubed. Plus, remaining is 2l times, you swap the order of the summation. J is smaller than l, I runs from 1 to n, aij, ail. So what's this? This is exactly as the jth row dot product with lth row. I mean jth column dot product with lth column. maybe. This row dot product with wait, column and row. I'm a bit confused. Here, column. Sorry. Here, this column and S column, and which is 0. So it's at most n cube. So that says that the summation of all the entries is at most n to the 3 over 2. So this shows that this cannot be improved too much, and then this order is best possible. So in the next video we will learn another method which is called alteration method. So not just considering the expectation itself, we can actually modify our random process a bit. Yeah, I will explain about this in the next video instead of talking about this in here.